Okay. Um, can you hear me now? Because it seems to say it's working. I think it's working. Cool. Great. All right. So we're finally back at Shenzhen IO. It's been a few weeks since I last streamed it, but we're gonna continue with it. Um, and part of this, I've got the next 2 weeks free until my next contract starts. So here soon, we're gonna kick off a new project and do Man to Tetris. And I can talk more about what I'm planning later. But yeah, this email, this is a funny email. I'll go ahead and read it for the stream, but it actually sounds like a lot of fun. So the electronics wet market is as sexy as it sounds. That doesn't sound sexy to me off the bat, but this does sound. Here we go. One thing I always tell people who come through Shenzhen for various reasons is to check out the electronics part market in the Huangjiang area. It's insane and super interesting, even if you aren't here for electronics at all. Imagine your traditional Chinese wet market, bustling with activity, hundreds of stalls bursting with everything you can imagine, except everything being exchanged is electronics parts. Substitute the smell of fresh shoulder for frying oil. Think of digital trash littering the streets into food scraps. And it's not just a few parts, okay, but every type of part. Like, there are entire markets dedicated to insanely specific things like batteries, say, or LEDs. It's a continuous white hot exchange of every manner of anything electronic. And craziest of all, these guys represent manufacturers who are also right there. You could find a part from a dude, ask him if he can supply your company with 1 million of them later the same day, and they could. It could happen. Okay, so that actually sounds really cool. I'd like to. I would like to get more into electronics IRL and build stuff. It's part of why. Part of why I am playing this game. But also I got a book recently, and I'll just show it to the camera. This one, Open Circuits. And this book is really interesting, full color. All it is a bunch of electronics parts, and it shows like how they're made and what they do, how they work. Um, but mostly it's just cool that it's a bunch of like the internals of various parts. And I'd like to understand electronics more. I feel like electronics, or just gear in general, used to be a lot more interesting before everything just became microchips. Like if you look at old videos of how like just weird mechanisms for like anything people produced. It used to be so much more interesting before it just became like, oh, just stick a microchip in it and program that. Um, but I think a book like this brings some of the life back into that, and I'd like to get into the nitty gritty of how those work. Um, yeah, so this email, I try to convey the scale of that kind of thing to people who haven't seen it, and it just doesn't come across. Oh, a market, that's nice, is what people would say, especially back when I lived in Vancouver. They're probably picturing something like the local ham radio swap meet they were dragged to when they were 5. They didn't get it. You won't get it unless you see it. Go see it. Okay, I might have to look that up because that sounds fun. That sounds interesting. Um, but on to our next product. So we have a precision food scale. Great working design. Okay. Yeah, we haven't started this yet. Okay. Are you aware of the system of precise dieting? This trend, which originated right here in China, has people across the globe measuring down to the milligram what they put in their bodies based on the ancient principles of yin and yang. Actually, my fiance, Shomei, and I have been trying it for the past month or so ourselves. It really boosts our stamina. I believe a portable food scale aimed at precise dieting community would do quite well. Okay. Simple. We can include a tare function to zero the display when the power button is pressed. Stamina. Yeah, good question. Sounds like Huel. Yeah, Huel, we already have Huel. It's already like precision engineered. I don't measure it down to the milligram, but um, it works. I know exactly what I'm putting in my body and where it came from. Okay, let's try this. So we're making a scale. Um, there is one button and weight. Weight is a simple input connected to an electromechanical scale calibrated for grams. Okay, so we get weight and grams coming in as a simple input. Button is simple input connected to power slash zero. Okay, it's just one button for both. And we just tare when we power on. Display is an XBus display corresponding to a numeric LCD screen. The scale is initially off, but can be turned on by pressing the button. What does on look like? I guess while the scale is on, the display should be updated with the measured weight. If the display is showing a value other than 0 when the button is pushed, the scale should zero itself to the current displayed weight, so that the current displayed weight is 0. Okay. Wait, when the button is pushed, so like every time it's pushed? So is it only like an on or off button? So it starts off, you push it, and that turns it on, and also zeros it, right? Am I understanding that? If the display is showing the value of 0 when the button is pushed, the scale should turn off and clear display before sending it the value 999. Oh, okay. So it only turns... So I see. It tears unless the weight is 0. And if the weight is 0, it just turns it off. And then the next push turns it back on. I see. All right, well, let's start with a basic chip here. Well, we actually have some state that we are tracking. And I suppose that's the weight. No, we are tracking the offset, whatever that is. So when we turn it on, I suppose we don't initially tear. Okay, so we need an accumulator that will keep the value of our offset. And when we initially turn on, I think we're going to pass away the weight. Let's see what's going on here. So the button, this turns on and turns back off. Fine. The weight starts changing, yada yada. Oh, and when it first turns on, it's at 0, but the weight's also 0. Now the second time it turns on, well, the weight is also saying 0. We turn on and off, sure. Oh, no. Simple input 0. Right, the button is pushed once, and then it starts at 0. And then the weight changes a few times. The weight goes back to 0. We push a button, this would turn it off. So the display is off. And we turn it off by sending -999. Okay. Then we push this again, it turns on. We put some weight on it. Great. We push the button again, and it zeroes that. The weight changes a bit. Cool. Now in this case, do we ever turn the button on when there's weight? Like here? No, here we're tearing it. So I'm assuming when you turn it on, you can just pass over the weight, and it seems like a coincidence that the weight is always 0 when it's turned on. Hopefully you don't have to tear it immediately. I don't think you do, but if that turns out to be the case, we can do that. All right. Weight is a simple input, And the button is also simple input, so we can do that. We can do that this way. And then we'll just send X1 straight there. This chip's probably going to be too small. We'll see. So we basically have, we'll have some loop where we sleep. Yeah, we sleep for 1 second at the end of every loop. Man, I forgot how long. It is sleep 1, right? It's been a while since I've done this. Okay. Well, we're gonna sleep 1 at the end of every loop and go back. And then we're gonna check if P0 is on, and in that case, oh man, I forget all my branching commands. We need to do a review of our instructions. Okay, so we have a test equal. Great, we can just test if our P0 test equal P0 to 100. 100, that means it's on. And in that case, we just send wait. So move wait, which is going to be P1. We can move that to X1. And then we'll sleep. Oh, and then that turns our state to on. And as long as it's on every loop, we need to continually send. So we'll need to save the on state somewhere. Yeah, I'm gonna upgrade to a bigger chip so that we have another register. Okay, so still the same idea. Instead of testing if the input is at 1, I'm going to test if our data, I'll use data to save our on-off state. So if our data is 100, so I'll leave a comment saying that we are on. And as long as we are on, we move P1 to X1. Okay. When P0 is 100, that is going to turn us on. Well, if it's also the case that data is 0. So if P0 is 100 and data test equal data is equal to 0, so we're off. So we have a button, we have a press, we'll say PRS. So we press a button and we are off, then we turn on by moving 100 to the data register. And then we check that we're on, and as long as we're on, we do that. Then on every loop, we sleep. This is X1, this is X3. Okay, so I think that's what we need besides the tear function. Let's give it a shot and see how that looks. Okay, cool. We are updating the display. Great. Now we need to be able to turn off when that button presses. Or tear. Okay, so we test if the data is all right, so we turn off if it's already 0. So I suppose, well, no, we just have a different branch here. I'm hesitating here because I'm thinking about putting the conditional negative, but we fall through to this negative if either of these fail, right? So if either of these fail, then what case is that? Then either like the button isn't being pushed, in which case we should do nothing. What we need is like a rising edge detector, essentially. Because our minus case is going to handle just all the off cases. It's not just going to handle all of this. So maybe we need to jump. If we're 100, we jump to a different branch where we start testing the other cases. Okay, so what do the other cases look like? We have something like this: test equal weight, which is p1. If p1 is 0, then we turn off. So move 0 to data, and we move -999 to our display. Right, so this turns it off, and that's the other part turning it off. Okay, so this is the turning off bit of code. And then we have a tear case, which I'm not thinking about yet. Now, basically, at the start of this loop, we go to a button case. We're going to go to a button case if this is 100. So here we're going to jump to the button label. What are our jump commands? I think it is just JMP to label, yeah. Jump to button. And we're gonna have a button label. Okay, yeah. Definitely tell me about it. Have I told you about my idea for a game that I'm spinning through my head? It'll be related to this project I'm working on with this Nantu Tetris. Related-ish. I think I could reuse some ideas. Yeah. Okay. So when the button is pushed, so this is our positive case here. Okay, we check if it's currently off, and if that is the case, then we move I guess we have a negative case that just goes to a loop. So like otherwise we jump to loop. I'll refactor some of this out. So when it is currently off, we're going to turn it on, and that's it. But when it is currently on, then we're going to test if the current weight is 0. And in that case, we do these two things. Okay, but now we're chaining those in a way that's not good for us. We'll need to do another jump, I suppose. Okay. I can bite into that idea. achievement that fewer than 1% of players achieve. Okay. So the off case is straightforward. This is a 0 case, and I think we can just put all into a negative, right? Yeah. So we move the 0 to data. This turns it off, and then we move the -99 to the display, and that lets the user know that it's currently off. Great. So we have our on and our on case when the button is pressed. Otherwise, we have our main loop. I needed a better name for this. So this is kind of our pass the weight, right? So we'll give this a label way. Great. So up here, we only jump if the button's not being pushed, then we go to the way label. All right. And if it is being pushed, we fall through into this button. We check if we're currently off or on. If we're off, we turn it on. If we're on, we turn it off. Oh, right. If we're on, we have to choose if we're tearing or not. So we can... We can't rely on this test here. Okay, I'll give this a label here. We have an off label. This is what we do when we turn things off. We do that move, we do that move. So either we turn on or we perform a test. And here's the thing, if it's a turn on case, then we're skipping this test and it's just gonna be plus by default. So we can't really use plus as a case here. But in the negative case, so this fails, it's not 0, then we're gonna jump to tear. So we check if we're off. Oh man, this is a pattern. This is a pattern here with the nested conditionals. I kind of forget. I've run into it a few times, so this should be standard by now. What do you have? So you have like a self-reflection of gambling culture today with card pack openers and sports bettors. Yeah? All you see is your total loss climbing as you keep playing. Oh geez, too real. Yeah, gambling culture is yeah, you can definitely pump out a game like that. I've had a chance to think more about gambling culture now that I've been playing poker often. And the more I think about it, like the less I like how much manipulation there is. Okay, this is getting too big. So maybe I just move like all the tear function off to a different chip. Like this chip can just handle the button stuff, right? And then some other chip can handle the actual functions. I'm gonna take a break from this chip here, and let's just see what the tear looks like. So we have some accumulator, and anytime we tear, what do? We're gonna take, we need to compute an offset. I guess I'll just be essentially like negative weight. So let's say P1 is the weight. And we might already have an offset. So we could just subtract P1 from our accumulator. Sub P1. Yeah, anytime the tear button is pushed, we sub P1. And honestly, that's it. I guess this chip can be the one that on every loop passes the weight to the display. Yeah, this chip over here is passing the input weights directly to the display. And here we should just be like move accumulator to X1. Or no, not accumulator. We need to do some math. So basically we're gonna take P1 minus accumulator needs to go to X1. And since our accumulator is where we do the math, we again need 2 registers, so we gotta do a big chip. Okay, so when we tear, we're gonna sub P1, and then we're gonna move accumulator to data. There, we have our new offset. And then when we show, what we do is move, well, we're gonna move P1 to the accumulator, and we're gonna subtract our offset. So subtract data. And then we're gonna move data to our output, which in this case can be X3. Great, so tear is like an optional thing. Yeah, let's put that directly next to our display. And then the other chip can handle telling this chip when we're tearing or not. Okay, so on every loop we can check our inputs. Let's say we're doing an input via X0. And sometimes we tear, but every time we show. So let's do a test equal on X0, and if it's 100, well, if it's not 100, we're gonna jump to show. Otherwise, we are tearing. And yeah, I'll be connected to something, we'll see. And then at the end of every loop after we show, we're just gonna sleep for 1 second and then go right back to the start. And I can clean this up a little bit, like all that can just be wrapped into a negative. and then we don't actually have to have a jump to show. So let's do that. So these are both negative. Okay. We'll leave the labels there because it's easier to read that way. Every time we show and then we sleep. Oh, we are not showing every time though. Right, we're not showing every time. We do still need to do tear on occasion. We need to do show also on occasion. And that would just be when we are on. So I can make our input here a little bit more complicated. So like 100 means we are tearing. Or not 100 means we're tearing. Yeesh. Okay. We'll do it this way. Okay, tear. So if we're at 100, we're gonna reset the offset. Otherwise, let's say 10. 10 could be our show command. Do we ever tear? Well, when we tear, we are going to show 0, right? So this can be distinct. So in this case up here, we then move 0 to x3 to the display. Otherwise, what we're asked to show, we do these 2 bits or 3 bits, right? Do our math with the offset and then move the display out. And if we're not showing, we're just gonna move -999 to x3 by default, and then every turn we sleep. Okay. Now this one here is handling the buttons. Way can be simpler here. So we're turning it on. We're moving P1 to x3. This thing, if we're having our input coming on the X bus, we can just sleep until X, right? So we turn it off, hit -999. And then once we do that, once we turn it off, we're gonna sleep on X0. Yeah. Alright, so like an X0 then would come in when we turn this thing, when we hit a button press, that's either turning it on or tearing. It's saying show or tear. And we show in a loop. So this would have like sleep for 1 second. I guess in the tear case, you'd also sleep for 1 second. So I think the first thing we would need here, I'm just gonna pull out another chip because I want to refactor. So the first thing we would need for sleeping on X0, we need to know if we're turning it back off. I'm not sure if I'm liking this design, making our whole layer of messages that we're passing in. Let me look back at the first chip first. I have to think about this. Okay. So first thing we'll ever do with the inputs is we look at the button. And then we have to decide whether that button is an on, off, or tear. We'll just start rewriting that here from scratch. So we can have a chip that just handles state changes whenever the button is pushed. And when the button's not being pushed, I suppose we just pass it off to something else. That something else would need to know if we are on or off. Okay, so button is pushed. So test equal P0 to 100. So this means we have a push. And when that happens, we need to determine. We need to first determine if we are turning on. So test equal test. And we're only doing any of these determinations when there's a push. So I'm gonna put a no push jump here. So jump no push. So we have a label no push, and we do other stuff down here, right? And then now we need to start doing other tests. So test equal data equals 100. So if we are, or data equals 0. So if we are off, then we need to turn stuff on, right? So like move 100 to data. Otherwise, the data, otherwise we were on, and in that case, we need to decide between, well, jump to, this is our maybe tear case, right? Like maybe tear. We'll call it that for now. So like we have this case here, and then we need to distinguish between tearing or not. So we test then if P1 weight is equal to 0. And if that's the case, we turn off. Move 0 data, and we are turning off. Otherwise, we tear. I'm just gonna say move 0, 0 for now, but this is us tearing. So there are the 3 cases for the button. We are turning it off, or in the case we're off, we're turning it on. In the case that we are on, we're doing another test. Man, I wish I had a nice way to squish all these tests together. So if our P1 is 0, that's our weight. We need to turn it off. Just say like 0. Yeah, we're 0 dot weight already. So this could just be the tear function, and what tear does is it either does the offset or turns everything off. Which is what we have going on here. And whenever there is no push, then we are basically just gonna like sleep for 1 second and then restart the loop, right? We could direct a chip to push out the current weight. And that has to be a different chip because we don't have enough registers here to track that state. So when there's no push, if we are on, in both cases we sleep, but if we're on, so test equal data to 100. And I know we move like 100 over to x3. This is our signal to pass the weight. So this is like show. Otherwise, we kind of just do nothing. And now this tear function, this could be similar, like we move 10 over to x3, tell it to tear. Otherwise, we tell it to show. Okay. Now this test equal P1 to 0. This is wrong. Because what we do is when our display output is 0, that's when we go to sleep. So this makes me want to move it over to the other chip. And the other chip would have to tell us back if we were turning it off or not, because it's the other chip that maintains the offset, right? This chip only maintains the current state. And as we saw here, if we're maintaining the offset in data, like we still need the accumulator register for performing our math in. So we can't do that over here, or we give up the accumulator. If I could calculate the offset just with the accumulator register, that'd make this whole thing a lot easier. I don't think we can, right? Because what are we doing when we tear? We subtract P1. Then we move the accumulator to data. And we need to move the accumulator to data because when we show, we need to do some math in the accumulator register by moving P1 to the accumulator and then subtracting the offset in data. Okay. So in this whole case, we don't even need to be testing if P1 is 0. Our maybe tear is just going to be this move 10 over to x3. Right. So if we're currently off, then we just turn on. Otherwise, we tear. And when we tear, we'll need to sleep on x3 to hear back from the other chip. So sleep on x3. That will tell us when we are off, I suppose. Well, I mean, if it's a tear, yeah. So now we test our x3, and once we sent that command over to the other chip, then either it teared and we're fine. So like if it's equal to 100, then we're still on. And we do nothing. Otherwise, let's say it's otherwise, let's say we get a 0. In the case that we get a 0 back, that means, hey, we turned off. And I suppose we can move 0 over to our data. Okay. I think we can remove this old chip. We aren't really using P1, are we? Yeah, this chip only handles the button input and tells the other chip what to do. Great, so let's review. We're testing if the button's even being pushed at all. If it's not being pushed, we just continue to sleep. Wait, what's this? Test if we're on. Oh yeah, if we're currently on, then I guess we move 100 to x3 to say like we're showing. And I guess that chip has to respond back, doesn't it? Yeesh. So like sleep on x3. Yeah, sleep on x3. I'm not sure if I like this, but we're going for it. And then we're gonna move x3 over to nil because we don't care how it responds. We just care that's done handling our command. Nil is an invalid register. Let me set it to null. Okay. Okay, so if we're not pushing the button, then we check if we are... I don't like that we're having to check if we're on. If we're not pushing the button, we check if we're on. If we're on, we're telling that thing to show. And waiting for its response. No, I think we only need to talk to the other chip when we're pushing the button and turning it on. So in this case, I'm going to turn this whole thing into just sleeping. So if we're not pushing the button, we're just sleeping and waiting for some button push to come out, right? That's all we're handling is the button pushes. Great. So there's a button pushed. We are currently off. Then we tell the other chip, hey, we're waking up. By moving, well, first we tell ourselves that we're still on. Yeah, we tell ourselves that we're turned on, and then we move 100 over to the other chip to tell it, hey, we've turned on. Start showing the wait. Okay, now if we push the button, and it turns out we were already on, then we tell the other chip, hey, try to tear, tell us what happened. And in the case that it's 0, it gives us a 0, we're turning off, then we are going to save that state and remember that we are now off. Cool. Okay, now this other chip here is going to work a little bit differently. I'll start a new one. So this is just handling the button. This chip is handling the wait and keeping track of the offset. So we're just going to sleep on X1. At some point, we get some input from X1. So we test X1. If it's 100, we are powering on. So let's do... in this case, I guess we just show on a loop until we hear from X1 again. This is the on signal. So this chip doesn't know when to stop showing. That's an issue. Hey, Nicole. So the other chip has to do that? Yeah, like this first chip has to babysit this chip until it receives another input. So if there's no push, right? Let's rethink this slightly. Suppose we have a chip and all it's doing is applying an offset. I mean, well, that's this chip, right? We want this chip to be continuously applying an offset. So like essentially this show here. We have this show function. We constantly move P1 to the accumulator. We subtract our offset. And we move the data. No, we move what's left in the accumulator over to X3. This is what it looks like to show. And that needs to be done on loop every second. So if this is a thing that sleeps, so show would need to be performed like between here and here until a button push comes in and interrupts that. So this chip then, if this chip is doing the show, needs to be checking every second what is coming from that input. Which means we can't do a sleep on the X bus. We'd have to do something more like P1 going connected to P0 here. And P1's giving us our command, essentially. Because show needs to be performed every second. Okay, so this is P0. So if P0 is 100, well, okay, we can't really send an on signal here anymore because then we have to be able to send an off signal, right? We need to send an on signal. We need to send like a keep showing signal, essentially, instead of sending just a turn on and loop your show. I don't know, like suppose we had a chip. Let's think of another design here. Suppose we have a chip. All it's ever doing is outputting the current weight, even in this case where it's off. And it's not outputting it directly to this. It'll be filtered by some other chip that gets a signal of whether we are on or off. Right, so it can be a very simple chip. All it does is figure out this offset, move accumulator over to X3 every loop, and we sleep for 1 second. Sleeping for 1 second has to be a part of show. Now part of the problem here is we like outsource the tear function over to another chip. Tear meaning maybe tear, like there was a button push. So this incoming input could be like telling us if it's time to perform an offset. There's input every turn, and it's one of 3 states. It's either 4 states, I guess. Yeah, there are kind of 4 things going on, right? So there's either 1, continue showing. There's 2, we're turning off. There's 3, we are turning on, which actually this chip doesn't really care about. And there's 4, we are resetting the tear. So if this chip can only care about three things, it is show the current weight. So on every loop, it's getting a command that says either show the current weight, or reset the offset, or send a negative 999. So when does this negative 999 happen? It is when the display is showing a 0, which means like the offset matches the whatever. Okay, so what happens when you try to tear when it is 0? Like nothing changes, right? You try to adjust the offset, you don't adjust the offset at all, which is fine. But in that case where you adjust the offset by 0, then now we're outputting negative 999. Or we only have to do it once, right? We don't have to do it continuously. Let's look at the information on this display. Display is showing the value other than 0 when the button is pressed. The scale should 0 itself. So we move P1 over to the accumulator, or I'm making this a little bit messier than I need to. Okay, so to take a step back, this chip only does one of a few. It will, by virtue of the fact that it is showing continuous updates on the weight here, it does have to sleep only 1 second on every loop, and we can't have any like sleep X and wait for input. I think even when we're doing the negative 999, I don't think we can do that. I mean, if we did do that, we could just wait for an on command. But now, like, part of our on loop is that we're also waiting for a tear command to come in. Right, so that's the show on every loop, but also on every loop we're gonna check so let's say we move P1 to accumulate, so we're gonna check if the button has been pushed. So like we test equal P0 is 100. And in this case here, we performed the actual tear. Let's try and put that in there. Okay, we have a tear. And tear is going to be followed by show. It's always going to be followed by show. So tear, we just sub P1 and then move accumulator data. And then, what was this idea here? Test if x0 is equal to 10. Yeah. We can remove these pluses. Okay, tear is always going to be followed by show, but sometimes we jump straight to showing. And that's all this chip does. Sometimes it gets a tear command. How does it know there's a tear command? Well, on every loop, it is checking the input. So test equal P1 is, or P0 is equal to 100. In that case, we tear. Otherwise, we jump to show. Okay. Very simple chip. Simple is good. We like that. And here's like an actual tearing function. But we need to make sure we know we are going to tear for sure. So let's say because the chip up here can't know whether it's valid to tear or not, right? So sometimes tear means turn off, or that input command means turn off. I'm gonna put off up here above chair. So when we turn something off, we basically just we move -999 to the output. Or what we could do, so when we show, we are always subtracting data. I suppose we could make our data so big that's always, oh no. The largest we can make it is 999. So like if there's a positive weight like 100 or something, then we won't be able to subtract that far. So we can't reuse the show function. And when we go off, we can't go to the show function at all. Okay, so we're gonna have a sleep here. When we decide that we're turning off, what we do is move -999 into the display. And it has to be this chip that decides between tearing and turning off, because whether or not we can tear or turn off depends on the data chip, on the current offset. No. Whether we turn off or not depends on the current display. And the current display is shown in the accumulator. Right. So the current display is I suppose we could move show P1 accumulator, subtract data. Let's take some notes here. Off means you move -999 to the output, right? Bear with me. I think I was on to an idea here of how we could collapse some of these cases together. So button push comes in when the accumulator, so like when the accumulator is 0 and button pushed, then we turn off. So in that case, we could actually move 999 into data, right? And then go on with our normal show function, because that, the first step is to move P1 to the accumulator and then subtract data, and then move accumulator out. Never mind. Right, because show is always going to be based on the current weight. Show is based on the current weight. Turning off is not based on the current weight, it's based on the current display. Okay, so if it's not 100, so the button's not being pushed, we jump straight to showing, right? Otherwise, we can do a test. And since that's a jump, we don't need to have a plus here. We can test if accumulator is 0. And in that case, we jump to off. And if it is not 0, so we don't need to jump to off because we're right next to it. So if it's not 0, then we jump to tear, right? Otherwise, we are turning off, which means moving -999 over to the output x3. But like on the next loop, it's going to think we're on again. And we need to wait for an on signal. Like maybe it is the best case just to go here, wait for an on signal to come in. And that on signal can come in from an X bus. Like what inputs are currently being used? P0. Okay. In that case, so we if we have a non-zero output currently, then we can jump to tear. And by current, this accumulator is like the value of the last output we just showed out, right? Yeah. Now I feel like we might confuse that a little bit because here's a place where we turn on and we already have a 0. What we're checking for really is for this tear function. This tear/off is what we're checking for in every loop. We can wait for the first on signal, and the first on signal we just jump straight to showing. So we sleep on X1. Yeah. We can sleep on X0, and when we only sometimes sleep on X0 though, and it's right after we've turned off here, right? And then this is, I guess, where we would first start the loop. Move -999 to 3. When we tear, we subtract P1 from the accumulator. So the accumulator has our current value. No, I think we want to subtract the accumulator itself. Well, actually our tear function isn't quite right either. So let's do an example here. Let's look at this example here. So here, yada yada, a pretty normal example. I guess data is 0 the whole time, or offset is 0. Here we get 16, we get 32, we get tear command. So now we've been asked to tear, the offset's 32, we're going to be subtracting 32 from all future things. Now when we were just doing our normal show, we were moving the P1 to the accumulator, we were subtracting our offset, and then moving that value on out. Right, so in that case, that's here. Like we have 32 in the accumulator. When we tear, 32 doesn't just become our new offset, it gets added to whatever our previous offset was. Right, so maybe we were already offsetting, you know, like an additional 16. Yeah, so we add 32 to that. So when we tear, then what we're actually doing is we take our accumulator value and we add data. So we add the offset to our current value, and then we move that accumulator to, okay. And then at that point, we also need to zero out our display. So move 0 to accumulator, and then we're allowed to show, and what we'll show is 0. Or maybe we don't, because now what happens is we move the weight into the accumulator. Right, so in this case it's going to be 32. And then we subtract the offset, the new offset we just made. It's going to be 32 plus whatever the previous offset was. Cool. So this is tearing. That's fine. We can tear by adding our offset to our current display value, moving that display value as a new offset. Okay. And when we turn things off, we simply move -999 out to x3. I don't love that. I'd love it if we could move -999 over to data. No, that's just not going to work. So it's going to subtract from the current weight. But still, we move -999 over to x3, and then we just can't do anything anymore. So then, like, the next loop comes in, we're still like testing for this button, and since it's not pushing, we should just jump to show, and show is gonna do move P1 to the accumulator, subtract data, subtract -999. That's gonna max us out to 999, unless the weight is somehow negative, which I don't think can happen. No, that can't happen. So we could do a case here where if it's 999, then we move -999 over out. Yeah, we could do that. It's slightly hacky. I think it works. So test equal. So we subtracted data. So if accumulator is equal to 9 and 9, then we move negative 999 over to x3. Otherwise, we just move the accumulator over to x3. And in this case, then we're just moving negative 999 over to data. Great. And then at some point, we actually hit a button. And it's going to jump us to tearing instead of turning on. And this can't all fit in here, can it? If we also have an off-on fashion, we're already loaded up. So we need to split this between two. Okay, so if we simplify this chip, what parts do we want to remove here? I think we can't handle the off function here. And maybe some other chip can do the sending of negative 999 out here. I'm going to take this back out. Our show's functions could be more straightforward again. Okay, when we show, we look at the current weight, we subtract the offset, and then we move the result out to the display. All right. So if we're not equal to 0, we're tearing. If we're equal to 0, we're turning off. So turning off means that we go to we send the X3 out. I'm still wondering if some other chip can have the job of sending that out. But turning off basically just means we wait for an on command. Like that's the essential part. Whether this does a negative 999 or not, then this needs to sleep on X0 until we are on again. Move X0 to null. And that's us turning back on. Okay, we move negative 999 over to X3. We sleep waiting on X0 for something to turn us on. And then we turn on. And once we've turned on, our first order of business is just to jump straight to show. Because we can't be tearing because we're turning on. So we don't have to worry about anything else. We're not turning off, we're not tearing. So we just jump straight to show. Do I watch Technology Connections? Yeah, I do actually. I often use Technology Connections to fall asleep. Like very watchable and very interesting. I don't mind if I don't catch all the details, and very easy to like lull you into sleep, I think. What makes you think of him right now? Okay. This is all good. Now we just need to be sure that we're starting at off. So like this here is our entry point. And then this checking that is our like loop behavior. We're constantly checking if the button's being pushed in like a normal way. In like, well, in a maybe tear or maybe turn off way. So that's like the tear or off button. Yeah, yeah. I like those old-fashioned electronics. I like that it's not just microchip did this or that, and there's like a lot of interesting mechanisms. I don't know, like old cassette tape players and how, like how you dissect those and how those work. That's always interesting to watch. Okay, I think this here is workable. I just need to turn this into my entry point, and I have a command that can do that, but I need one more line in which to do that. So there's this jump to show. We have a jump to tear, so we're either showing or tearing. Otherwise, we're turning off. Maybe this P0 can tell us a little bit more. This 100 means that the button is being pushed. And we might need to tear, or we might need to turn off. And that depends on the current value of the display output. Can I combine these two tests together? Okay, is tearing the worst thing? Yeah, no, we definitely don't want to tear unless the button's being pushed. With the off, there's a jump to show. With the tear, we just fall down directly into showing. Can we somehow like combine the jump to show? Here we turn on. It'd be nice if we just fall directly into showing. But then now tear would have to jump to show if we did that. Well, this jump to tear doesn't even need to be a jump to tear, right? So our tear function can just be under pluses. So if accumulator is equal to 0, then we do these things. So this add data, right? And then move accumulator to data. Add the offset. Move accumulator to the new offset. Okay. So this is tearing. Right? So if we are pushing the button and we are not tearing, then we just by default go into the off case. Okay, great, we've saved enough space there. I suppose this doesn't need to be a label. And in either case, we're jumping to show. So we don't even need to have jump to show anymore, because we can just have this. We can delete this jump to show. So here's the off, sleep, on, and then we go to show. Otherwise we tear, and then we go to show. Great. And every time we show, we then sleep, and on the next cycle, we check if the button's being pushed, because it might mean we are doing a tear or turning off. And if the button's not being pushed, we just jump to show again. Perfect, we've got this. So our initializing command is just going to be jumping to this sleep case here. This here is just part of show. Okay, so we jump to sleep, and we're just waiting for input on X0 to activate this chip. And input only gets sent to X0 for this chip whenever we are turning on. That's this case right here. And the sleep X0. Wait, here we turn off. I mean, the other chip needs to know when we are off, doesn't it? The other chip does know. The other chip does know. Well, does it? Because it has to learn from this chip. Because whether it's on or off, whether it's off or tear, depends on this data register. Okay. The chips just aren't big enough to do like barf all the logic and then refactor it. Okay, but we are in a better spot, I think. Man, this is such like a simple concept, but I don't know why it's getting me. This is just not a way I'm used to coding it when I only do it once a month. Now what's going on here? I don't think I need this anymore. And back to this button handling chip. So the button is pushed. If there's no push, do we care? No, we just keep sleeping in a loop. Otherwise, we check if we are off, sure. We tell ourselves that we are on, and we move 100 over to X3 to tell this chip that we are on. So this is going to connect to the X0. Right? It tells the other chip that we are now on. And this is the otherwise case, the tear case. Cool. So otherwise, that's where this P0 comes in. This is a tear / off case. We move 100 over to P1, I guess. So, I mean, this chip knows that it's a tear. It knows that it's maybe tear. Maybe tear, maybe off. Yeah, it has to hear back from X3 to turn off. So this chip has to give some information back when we turn off. Let me just label down here. Let's call this S. because we need one more line so we can communicate back to the primary chip. Why is there even a negative? Oh, right. Okay, that's a problem. Because that's not going to start off negative, and it's just going to be completely ignored. So we need to take the negative signs out of here, I suppose. Which means there does still need to be a negative up here. When it's negative, it's okay to do this off stuff, right? This power off stuff. Negative here meaning like the we weren't zeroed out, so we're testing if we're 0, right? And if we're not, and if we this accumulator is 0. Oh, this is actually the negative case here. Yeah, we're tearing if it's not currently 0. And the positive case is tearing. Off sleep on. Is there some way that this chip can decide if we are on? I suppose every time we send a tear signal over to this chip, it could respond back with whatever that data is. But where is this going to store it? Because... okay, I think I need to think about my data a little bit differently, because if we can just have one data representing our offset that also is able to tell us if we're on or off, our life would be a lot easier, and we wouldn't have to split between these two chips in this awkward way. Let me think about this. We can't just... jumping straight to here is also a little bit of a problem. And the thing is, like, I wanted this to fall through to the showcase. I suppose we could start directly here. And the accumulator should start off at 0. In which case its first action is to turn itself off. Yeesh. No, we don't want that. Again, maybe the idea of determining from the offset. So if the offset matches P1, then we're going to turn off. Maybe off should just be like implied instead of actually tracking the state here. Right, like this whole move 100 over to on. So like we constantly check for being if we're pushing a button. If there's no push, we just sleep and move on to the next loop. This jump S here won't really do us. Suppose this is our main chip, right? P0 is just telling us that the button is being pushed. If the button's not being pushed, we jump straight to showing. And the current problem is that like we will always show even if we are off. So how do we actually turn off here? Well, we tried to tear, and we're like, there's nothing, there's no tearing to be done. I suppose instead of checking if accumulator is 0, I mean, yeah, we'll do that. But data equals the incoming weight. And we could special case the data to a value like -999 or something. Which means whenever we try to do the offsets, we max out the scale, and that tells us that actually we're still in our off state. Man, this thing's not even supposed to be on. Why does it still have inputs when it's off? It's still doing math while it's off. It's like our smartphones, they never really turn off. Alright. Hey there. You work with both low-level languages and very high. Well, thank you, thank you. But I don't work very well with this assembly. Okay, you know, I did really well with TIS 100. I'm proud of my work there, but I've been struggling a little bit with Shenzhen. Thing is, both this game and TIS 100 are not really just writing assembly. So like just writing the assembly is the easy part. But they both have different things that make the puzzles interesting aside from the assembly. So TIS 100, what you're really doing is working with like a miniature actor system. So you're doing like distributed programming, and you're like coding it in assembly, but like the assembly is not the interesting part. The interesting part is that you're doing like distributed computing, and all your nodes are so tiny that you have to figure out how to distribute that computation. And that's what makes TIS 100 interesting or difficult. Not the fact that it's like assembly. And here, I don't really know how to say that about Shenzhen yet. Like, I guess it is also distributed computing. But here with Shenzhen, you're doing like a lot of there's like a lot more state that's being distributed between these pieces, and that's what makes it tricky. And of course, like this particular brand of assembly is weird to work with. Like I struggle a little bit with the way conditionals are done, because each chip just has a global like true or false, and every time you do a check, it changes the state of that global true or false thing, right? So you can't really do like nested if-else branches, because whenever you do a check, you know, again, it's like global. Well, the thing is, for these boards, you only have like 14 lines of assembly, and I don't think even, I don't think Rust can compile to like that small of a thing. But even then, like I don't know that it would translate to the same kind of assembly. Like this is a very weird dialect, I find. It's not like the assembly that like your C compiler normally translates into. Um, yeah. Okay, so like what we can do here is every time we tear, every time we handle a button press, we can send the offset back to this chip. And this chip yeah, so like this chip could handle like this chip can be the one that handles the sending the negative 9999, the default case over here. In fact, let's just open up a new design. I'm gonna copy this over and start over. Well, not start over, but like we have a save state here. So if we have this chip here on the left, well, let's start with this chip here on the right. So let's say this chip on the right handles pair / off, and it will always sends back the offset. And then this chip here handles on / off state. So this chip then can just sleep when it is off and wait for more information back from the primary chip. And then this chip can handle sending neg 999 during off state. I promise it's not too bad. Like the assembly here is very very small, like much smaller than a typical assembly instruction set. But like the quirk here is like whenever you do any of the math operations, it gets done, it gets performed in this accumulator register. Right, but we only have like add, subtract. Oh, we have multiply. Add, subtract, and multiply for the most part. Not. I don't think I've ever used not. And then like isolate specific digits or whatnot. And then we have like the control. So like we have all these tests that change the global positive negative flag. And that's about it. There's not much to the language. Got the weird conditionals and a couple basic math operations. Hey, Sparkly Dark Matter, good to see you again. Yeah, I had quite a lot of work in the last few weeks. I was really so it's a tax season rush had me really busy then, like a lot of work at home. But I'm back. And I'm wanting to start the Nancy Tetris, so I think I'll start doing that next week. And I think in the meantime, up until then, I'll do a run through of MicroHard, MRHD. And that, I think I should be able to run through that in like 5 hours. It's basically the first half of Nancy Tetris turned into a video game, which is basically like use a hardware design language to implement the the CPU. But the part I want to do on stream in code in Scala is building the actual emulator. An emulator for that CPU, and then the virtual machine on top of that, and then the compiler. So that will be the project, and we'll just like speed through the first half by doing it as a video game version. Oh, it's MHRD. Okay. So let's look at this again. I think we have to do a slight change. So we have an off case here. Now, if this thing, so let's say this is the chip that computes the offsets. It performs the tare. It also does the showing function. But now, if it's doing that, it also has to return, like every time a button is pushed and sent over to this chip, it has to send a result back to the first chip, because the first chip is going to handle the on-off state. So here's the thing though, like when it handles that, if this chip itself is not aware of on-off state, then it has to sleep during this. And during the rest of it, it has to be like a hot loop checking every 1 second. And that's kind of like the main thing I'm struggling with this design. Because it has to wait for those button presses, and the button press might be a tare, it might be an off. And if off means sleep until it gets another thing, then it itself has to be aware of the on and off state. Man, I'm not sure how to split this between these two chips. So this is a tearing function here. I'm pretty satisfied with that. This is the turn off section. And we can't just send everything over XBus from this chip and await I guess it can await a response. No, it can't, because if this handles a button press, it can't block waiting for this to finish its deal. Like this needs to be, the other chip needs to be running in a hot loop, displaying all this stuff. Okay, so then we'll do it this way. This second chip will just be in a hot loop all the time. It'll always be checking this button press from the outside. Sometimes it turns off. And it turns off, I guess, not by sleeping. But it needs to tell the other chip that it is off. That way the other chip can, I guess, tell it that it's off. So like we could do a test. If it is some value, then we are just continuing to show the off display here. I don't know, let's do like a high level version of that. So we're getting data in from P0. Most of the time it's 0. But in a 0 case, we aren't just showing. So here we have it defaulting to showing. This show needs the capability to do -999 if we are in fact off. Oops. maybe we put that here. So show move P1 to accumulator. We could have, this is like checking the weight, doing the offset, then moving that out. We have 2 more lines of code that we could use, so we could do a test. I suppose we could test the sleep and on. Let's remove that. If we can somehow use the data register, so let's say we also move -999 to the data. And now when we're showing, so I guess this thing, we have a special value for off, and when it's on is when the offset matters. Now the offset is always going to be positive, right? Yeah, like a negative offset shouldn't be possible because the weight could never be negative. The incoming weight can never be negative. So we can do a test here. Test equal if data is -999. And in that case, we move data over to x3. Otherwise, we use the data as an offset. So all we're doing when we turn it off then is we move -999 over to the data register. And we don't need to do anything else. Okay, and since this whole thing starts off, we can have an initialization here that says move -999 over to data. Okay, now when this button is pressed, I guess we need the ability to turn it back on. But let's see what happens right now. So when this button is pressed, then we check if the accumulator is 0, in which case we're like tearing, sure. That'll be the like default behavior. And otherwise, we tear. Interesting, so we could turn it on by performing a tear. So we could do something slightly hacky here. So we add data. Data is -999. We add -999. An accumulator is basically whatever the display value currently is, right? Add -999 to that. Nope. Okay, so we need a special case then. If we are currently off, then when that button is pushed, we turn back on by setting accumulator to 0, setting data to 0. Setting accumulator to 0 and setting data to 0. Right, like we set the offset to 0 when we turn it on. So like basically when we turn it on, we perform a tear. Well, here there are cases where we turn it on. Well, there should be a case where we turn it on and there's immediately wait. It looks like every case we have in this test, at least, is we turn it on and the weight is already 0. And right now we're only distinguishing between the tare case and the off case. We need to just distinguish that we're actually turning it on. And we only have one more line of code. This is the tare, this is the off. Otherwise, if accumulator is 0, then we tare by adding data. So adding -999 or like subtracting that. So what we could do when we turn it off is move 999 into the accumulator. Then when we push the button, it's gonna be like, oh, we should tare, and it does that by adding -999 to 999. And that starts us off at 0. And then we move accumulator to data. That moves 0 to data. Like, that would work. That would work with our data set. And then we can just figure out the edge case later where you turn it on and there's already weight. Which might not be too bad. Like, I might just need to use actual weight value in here somewhere. Great. Well, now this isn't really using anything. Besides the button input, so we are down to 1 chip. Let's try that. I mean, no shot we got this with just 1 big chip. But, you know, we could see what happens. Oh, we are not sleeping. So there's that. This sleep needs to happen every loop regardless. Alright, we're not showing any display output at all. Because what's happening? We're checking if the button's being pushed. In this case, it's not currently being pushed. Which means we're just jumping straight to show, right? Yeah, we jump straight to show. We don't need to perform that. Well, okay, data is -999, so it thinks we're currently off. And we just move that -999 over. So we never actually turned on. We just keep sending -999 over. So let's start here from the beginning. And at what point should we turn it on? Okay, so we're saying a -999. That's fine. Okay, now we get this 100 coming in from the button. So the button comes in, and it is 100. Which means we don't jump straight to show. We do this check. So our accumulator is 0. And in that case, it is 0, so it's going to attempt to tare. It turns on and immediately attempts to tare. And it does that. Oh, no, it's turning off. It turns on and immediately turns itself back off. Okay, what happened? So we test if it's 0, and then we're like, okay, it is 0, which means we need to turn off. Right. And the first behavior I wanted to give it was to turn on. Or not to turn on, but to attempt to tear. So it's not great, but maybe we can special case this in here somewhere. So whenever we turn on, our accumulator is already 0. How do we know that we are in fact turning on and not trying to tear? Like the button's being pushed. It needs to skip both these cases. This conditional then needs to be like a 2-part conditional. So we need to check both that the accumulator is 0 and that we are in fact on. So data is not equal to -999. Let me just see what happens when we comment out this. This is the line that turns us off to start. Okay, so like we're sending 0 out, which is not what we want, but like it's to be expected. Okay, and then this button is pushed. And now at this point, well, it sees that the accumulator is 0. And it's going to try and turn itself off right off the bat. Yeah, that's not great either. Oh, no. Did it actually turn itself off the bat? Move 999 over to accumulator, and then we do the show. Which in this case will be, we test if the data is equal to -999. In that case, we send 999 over. Okay, so it has turned itself off. It doesn't know how to turn itself back on. Okay. Quick bathroom break, and I'll be back to this. I don't know. We'll give it a run. Alrighty. So back at this, what do we have here? We have a machine that wants to keep turning itself off right off the bat. Um, I think I would like to have another chip that tracks the current on-off state. And just to talk through the difficulty with doing that, like if we have that here, then anytime this chip delegates to this one here, then this needs to reply back when it's off. So we could have like the chip, first chip gets its on value, and it tells this chip, okay, you can go ahead and do stuff. And then this chip, okay, so if we were doing it this way, then both chips need to handle the button presses. So the first chip handles the first button press that says turn on, right? And this chip is waiting for a signal from the first chip. And now that it got that signal, it does all this stuff. And then at some point, it gets a button press, and it's like, okay, I'm gonna tear. At some point, it gets another button press, and says, okay, I'm gonna turn off. And that's when it delegates back to the first chip, and it just sleeps on the X bus. So we could do it that way. Yeah. I'll just move that down. Okay, but in that case here, then the first thing this needs to do is sleep on X. If this doesn't need to handle the off case, and this chip here is handling the off case, then we can just, what do we do here? We can remove this conditional check. So show doesn't need to check for our special case, right? Data can just be the offset. And we can delete these three cases. Okay, show is just doing the math and sending the result over. And this display does have an XBus input. Okay. That's fine, that's fine. So this is the tearing case. In fact, I probably have room for labels. Maybe I won't. But we'll leave the label in for now. So here's the tearing case, and here is the off case. Okay, and this lets us decide between tearing and off based on that. Now, we have a loop. We have our normal loop is to check for the button input P0. But that will exist inside the broader like sleep loop, I suppose. So when we're done, after we're done showing, let me make myself some more space. We're just going to jump to our normal busy loop, which is to check the button. Yeah, we check the button to decide if we're stopping. As the button's not even being pushed, we just go straight back to the show, and that is our main loop. Otherwise, we are tearing. And I don't know, can I? The comment is fine. Otherwise, we're tearing or turning off because we're handling that button with either a tear or a turn off. And turn off, we don't want to be doing the work of turning off. That's going to be the other chip's problem. So we'll probably have to do some sort of reinitialization. So we could like move 0 over to accumulator or move 0 over to data. We're setting our offset back to 0. And we're going to jump back to, I guess, the start. And start just means sleep waiting for x0. And we're going to move that x0 value to null because we're not just going to use it. We're just going to use it to wake up. Yes. So we're going to jump to start. Okay. Otherwise, we jump into this inner loop. Well, this we can't just jump to start. I suppose we should send information back to the first chip. Because while this chip is doing all of this stuff, the first chip's just ignoring button presses until we turn off. Then the first chip can... So the first chip is going to be sleeping while this is doing that work, right? So... Well, we do still need to reset. Maybe we can find a fancier way to reset this chip. But let's say we move 100. Yeah, back over x0 and jump to start. So we tell x0 that we're done. Great, that works. Okay, so this chip here has its own busy loop. It's simpler because we're just waiting. At first, we're just waiting to turn on. The very first time we're waiting to turn on, and then let's see. Once we turn on, we like delegate to the other chip, and then we wait for the other chip to tell us we can turn on. Yeah, we wait for the other chip to tell us that we're off. And from there, we are back in our busy loop waiting to turn on. Okay, so we're checking if we're on. Let's see, test equal p0 to 100. And one is 100. We're just going to move 100 over to x2. And then we're going to sleep waiting for x2. And then we continue our loop. So in all the other cases here, we do nothing. Yeah, we just sleep for 1 second, I guess. We're waiting for that p0 to equal 100. And then when it does, we send that signal over, yada yada, and we get back into our sleep loop. Huh. Very simple chip, I suppose. Just take a look at what that does. Part not sleeping blocked on right. Move 100 over to x0. Oh, we have to do something with that value. So we sleep on x2 and then just move x2 to null for now. Okay, which chip is even active right now? Well, we've got the off case. Oh, right. The off case So if the button's not being pressed, or we're doing anything else, we're just moving -999 over. I guess you only need to send -999 once, and that clears the output. Let me just check the manual. For that like LCD display. Okay. So it can write any of these values. Oh, that's good to know. Like we max out 198. So if we write -999, that turns off all segments. That just needs to be done once. That doesn't need to be done on loop. Okay, that is good to know. Alright, so part of that then, move 100 to x0. I guess when we get that from the null, then this chip can handle the job of sending a -999 over. I'd like this chip to do it, but let's see what actual issue we were running into when we were doing this. I'm not sure. So this is in a sleep loop right now. No. It seems like they just take turns sleeping. Okay, so this chip starts by waiting for x0, right? This is just sleeping, waiting until it sees that button push. That button pushes. Great, so now we're going to move 100 over to x2, and that will allow this one to wake up, this second chip. Great, secondary chip is waking up. And now it's in the main loop. So it's testing P0. Well now that's a problem. When it first wakes up, it shouldn't be noticing that button press, because that first button press is supposed to be handled by this first chip. So perhaps this should start when it wakes up by sleeping. But we don't have room for that. Lazy Schemer, welcome. It's been a while. It's going all right. I'm struggling a little bit with this problem here. I am super rusty on Shenzhen. But in a broader sense, things are going great because I have 2 weeks off. And I'm wanting to start my anti-Tetris project. So I've been doing some reading and planning for that. And this week at some point, I think this week, I'm gonna just do a speed run through Microhard, which is like the first, it's like the part 1 of anti-Tetris as a video game version. But I don't know, maybe I save that for next Monday evening. Okay, so this problem here. So we have a button. This is just a weight scale, and the button does 3 different things. So it turns on, or it tears. If it's already teared to 0, then the button press means we're turning off. So there are 2 pieces of state that we're handling, and one is like whether we're on or off. And I wanted to give that bit of state to this chip on the left, the primary chip. And the other piece of state that we're handling is the offset for the tear. And I'm wanting to have this chip handle that, right? Now, once we have all that logic for handling the offset, there's not much more room left on this chip. So like, that's why I had to split this logic between 2 chips. And I'm trying to have a situation here where I have each of these chips sleep in turn. Like once it turns off, this chip is just waiting for the on signal and sending it over. That way, this chip doesn't have to do as much work. It only has to handle 2 cases of the button press. But what I've done right now is that when it first wakes up, it sees that the button's being pushed, which is not good because it then interprets that as an off signal. So what I think I might do instead, move 100 to X2, we're gonna sleep. We're gonna sleep here for 1 second before we send the signal over to this other chip. That way it won't, the button only shows up for 1 second. That way it won't see that button, that on press button, and think it's an off press button. Kind of hacky, but maybe like we can build something on top of that. Oh, okay, look, it's doing stuff. It's showing the weight. It's tearing correctly. Cool. Cool. Cool, 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 cool. Right, now the only thing we're missing is the zeroing out of the display. I suppose when this turns off, let me label the off bit. So this means we're turning off. So when this turns off here, this chip can be in charge of sending -999 over. So we can move -999. Just I would love to do it on this chip on the right, but we're out of lines of code. So we have to have these hacky solutions. Oh sure, yeah, I'll have a look at that. Okay, so we're gonna move this over X3. Yeah. Okay, I need to make some room in my wiring here. So we're gonna do this. Okay, and now this over here. E0 is not connected. Oh, shoot. We don't have enough room for that. We don't have a ton of room. I can move this down 1. There we go. Okay, this is still going out on X3. All right. Let's give that a shot. So we are now zeroing out correctly. But when we turn on after zeroing out, we're showing the wrong value here. So let's slow it down and see what's going on there. Okay, so here we turn on. And nothing was sent over to this, right? Because we had that 1 second delay. Now the secondary chip is looking, it's activated. And it's looking for a button press. There's no button press. So it's jumping straight to show. Right? So we subtract the data and it calculates 0. And at this point, it moves accumulator over. Okay, so it is showing the 0, but it is showing the 0 1 second late because of our hack here. Okay, everything is fine except it's showing the 0 1 second late. I could have this first chip do that. Look, every time it turns on, it's 0. So we can at least pass this test case. Well, luckily for you, I have a hacky workaround for that. So, it's doing the sleep one. First thing it's going to do is send the signal over for this other device. And it's just going to move 0 over to X3. Okay, it passes the tests. I don't think it should it shouldn't work in normal, like, if the device wakes up and there's already weight on it, it shouldn't work. But that's not one of our test cases, so we pass. Oh my god, what a mess. Well, our power usage is great. Look, a lot of people did do it in one chip. So our cost is 10 yuan, and you should be able to do it in 5 yuan. And we have too many lines of code. Or 4 yuan? 0, 1, 2, 3, 4. Continue editing. What's the cost of this big chip? 5 yuan. Okay, we should be able to do this in just one big chip. And that's what I can't figure out, is how to squeeze all this logic into just one chip. That's why we have this weird hacky workaround stuff. Oh, I so want to call that good. Because I want to start fresh on a new project and redeem myself now that I'm warmed up a little bit. But hey, we got to work. What's gonna happen is what usually happens is after I end my stream, I'm gonna think about how to do this, and then I'm gonna have to like wait a week to actually handle it. But maybe we give it a quick look here first. So when it turns on, it is a usable workaround just to send 0 over. My on-off state is basically handled by passing between these two chips. I'm not actually recording the state anywhere. When we turn it off, we move 100. Yeah, when you turn it off, we're not really doing anything special. Interesting to see that's always 0 before it's turned off. Right, the accumulator is always going to be 0 before it's turned off, so it's already reset. So we don't need to do any resetting there. The only reset we need to do is to set the offset to 0, which we do here. Maybe I can do this as 2 small chips. No, we can't, because the way I'm using these registers, the offset has to be stored in data, in a data register. See, like, if we removed this sleeping and communication between the two chips, that gives us a few more lines of code. And maybe in those few lines of code, we could do what is essentially being done by this one chip. Yeah, I'm gonna go back and tackle that. Let's let that run. And let's get our praise emails. I think I need a little praise after that nonsense. Return to email. Splendid work. Well, thank you. It is my best work. This is truly the essence of... Is that our company name? No. Oh, of precise dieting in an electronic form, and another great example of the confluence of ancient wisdom and modern technology. I'm excited not only to introduce this product to the world, but also for his fiance to use it. Oops, sorry, I know not everyone here can read characters. This is my girlfriend, Shomei. Okay. Well, let's make a new copy of that. And I'm inspired here to try and remove this communication between the two. So let's take out this SLX. And here's okay, you know what? We could say when our offset is 0 and a button is pushed, then we are actually turning on. The first check we do is that accumulator is 0, in which case we need to turn off. That doesn't work, because if the offset is 0, it could be the first time we're running a tear function, and if we're running tear, I still have the PDF over the gameplay. Oh, thank you for telling me. Okay, so let's remove that. We're gonna try and get this down to just one chip. So we're not gonna do this moving. We turn it off. We don't ever reset the data register, the offset. I guess we never needed to. Let's do the verification here. Yeah, the first time the offset is never set. Here, the offset gets set to 32. And then I guess it's briefly negative 32 before we turn it off. Right, the customer has has been courteous enough to always remove the item. Oh no, this is tearing. So this tears. They are tearing it before turning off, which I guess is nice. So we don't need to reset the offset when we're turning it off. What do we do when we're turning it off then? We just jump to start? Well, I'm gonna move 0 to the data register because I think we might actually run into edge case now. So this is what it means to turn it off. So if the button's being pushed and our current display is 0, then we're going to try and turn it off unless we have evidence that we are turned on. And if we are turned on, how should we interpret that? Okay, so there are 3 button presses. So if we are off, then we go turn on, and if we are on, we tear / off, right? And how do we choose between tearing and off? Well, if AC equals 0, then we tear. No, then we turn off. All right. And how do we know if we're on or off? So when we tear, we're gonna turn, we're gonna set data to 0. And I guess if that is our evidence that we're off, so data equals 0 and accumulator equals 0 means we are off. That implies that we're off. That implies that we're off, and that means we're going to turn it on when you hit the button. And then let's say data is equal to 0 and accumulator is greater than 0. Then in that case we tear, right? This implies that we're off. What we're actually doing is we're turning on. So when you push a button, if data and accumulator are both 0, we can turn on. If data is 0 and accumulator is greater than 0, then we tear. But if data is equal to 0, so here's a case where data is 0 and accumulator is 0, we are actually turning off. So we can't do it that way because our on and off case looks the same. Well, if we turn it off, okay, the offset is always going to be 0 or greater while it's on, right? We can put a negative value to indicate that we are off. So let's say, let's say if data is less than 0 and accumulator doesn't matter. So if data is less than 0, then we are turning on. Data is less than 0, we are turning on. And when we turn on, we set data equal to 0, and we do like our normal show loop. And then we show. Okay. And then if data is greater than or equal to 0, then if accumulator then we handle the tear or off case, right? And if accumulator is greater than 0, we tear. And if accumulator equals 0, then we turn off. And off means we set data equals to -1. Data equals some value greater than 0 plus equals P1, right? And accumulator gets set to 0. Okay, so we can do something like this. So then the first thing we need to do is initialize by setting move -1 into data. Great. Now a button has been pushed. No button has been pushed. We just go to our normal show logic. That show logic should only work if we are on, actually. So we can't really do a jump to show. And maybe we don't first look if the button has been pushed. Let's do this. The first thing we do, test greater than. Do we have a test greater than? So we have our test instructions here. Yeah. Okay, so we can test if data is greater than -1. So it's 0 or greater. And if it's not, we just jump to the sleep loop. So jump to sleep. And I don't think we'll need this jump to loop at the end. Okay, first things first, we check if we're off. If we're off, nothing matters. Well, okay, something can matter. We're potentially turning on. So if we're off, we have an on spot here. So we could jump to turn on. And in order to turn on, when you turn on, data equals 0. So move 0 to data. Yeah, there we go. This is working. When we turn on, we move 0 to data. And then we do the show logic. So I guess on can go up here. On, move 0. Move 0 over to data. Okay. And then we do just show logic, which is move P1 to accumulator, something, yada, 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 yada. Cool. Well, hold on. That's on. We're not turning on yet. We're maybe turning on. If the button is being pushed. So test equals, so if P1, P0 is equal to 100, then we turn on. And then we move on to show. Otherwise, we just go straight back to sleeping. Hey, I'm going to remove this jump to start for now. So we move 0 to... And then we jump to... No. If the button's not being pushed, so we're off. If the button's not being pushed, then we just jump to sleep. Otherwise, we say that we're on, and we just fall into the showcase. Cool. Great. So that is handling turning ourselves back on. Now, otherwise, that's greater than plus equal accumulator to 0. So otherwise, we need to check if the button's being pushed. So and then we need to check if we are tearing or not. We don't need to be yeah, so we're already on. There's just not enough room. Maybe this isn't the way to do it. So we do have to check if we're 0 or not. And then this is our tear function. That is non-negotiable. We add data. Yeah, we add the offset. And then we save the new offset. So calculate the new offset, save the new offset. So this is tearing. And turning off means moving -1 to data. So we do still need to check that the button's being pushed. So test equal. Man, how do you do this in just one chip? I'll have to sleep on that. I'll have to sleep on that. Okay. What is this? Anyone ever heard of the PGA 33X6? A pushy stall vendor nearly stuffed these into my pockets as I was walking through Huajiangbei last night. No idea what he was saying. Have some NAF undocumented chips, I suppose. Well, I guess we have a bunch of them now. If anyone can figure out how to make use of it. Okay, well, we have an undocumented chip. And I guess that means it's not in the manual. PGA. Yeah, no, not in here. Oh, we'll have to figure out how that works. Cryptocurrency deposit terminal. We partnered with a major financial services company to create a cryptocurrency deposit terminal for people concerned about turbulence in the financial system. It should do especially well in regions where people are worried their government-issued currencies may be devalued soon. Interesting. The terminal reads an account number from a cheap magnetic stripe card, accepts a cash deposit, and sends the information to a bank over the internet. Because nearly all the money is flowing in a single direction, we just have to have it handle deposits. Okay, great. A deposit-only terminal. That can't be too hard, right? Okay, already we have a bunch of inputs. So we have 3 different cache inputs. Cache 20, 50, and 100 are mechanisms that detect bills. Network is an X bus connected to a network interface. And what do we have to send? The user initializes the transaction by inserting their account card. Okay, I don't think I have the mental stamina to do this one tonight. But maybe next time. Ugh. Okay, let's see who's online. We can do a quick raid. You've got people working. I think in design, right? Pre-spec. Here, let me show you what I'm looking at. Yeah, have a good night. It's good to see you here. Okay. I like the Coppinger's work, but I don't understand what this is about. Planning and design prep spec. Let's take a look. None of our usual folks are online. Who am I following? Hypergame Dev is sub only. Yato. Oh, I've got ads now. Maybe I don't do a raid tonight. we'll just call it a night. And yeah, hopefully do micro hard soon. Oh, Sparkly, are you still there? Because if you are, I want to show this book I got here, which is yeah, yeah. Thanks for stopping by. Okay, I'll just show off this book real quick. So I got this in hardcover too. Um, but this book is all about electronic components. So it shows it's full of all a whole list of these components. It doesn't go like into a lot of depth on each, but what it does show is like it shows them disassembled and explains a little bit of like how they work and how they're made. So this book is called Open Circuits. I've just started reading it, and I don't know, it ties into Shenzhen a bit. Um, and it's really cool to have as like a hardcover because it's like a nice coffee table kind of a book. So I'm just gonna put this out as a recommendation to check out, and then I'm gonna call it a night. Thanks for stopping by.